Today we are going to discuss some numerical problems on oscillations. In the numerical, it is given mass of 10 gram is acted upon by a restoring force of 5 dyne per centimeter and a resisting force 2 dyne second centimeter inverse on. Find whether the motion is periodic or not and what value of the resisting force will make the motion critically damped. So here the mass and the restoring force and the resisting force, that is the damping force, is given. We have to determine whether the motion is periodic or not and the value of the resisting force which makes the motion critically damped. So according to the problem, we know the expression of restoring force which is directly proportional to the displacement can be written as F restoring is equal to minus AX, A being the force constant, and it has unit Newton per meter in SI system and dyne per centimeter in CGS system. Then we have by comparing this equation with the given data that the restoring force is 5 dyne centimeter, that is the value of A is given actually. In addition to this, we know the damping force is directly proportional to the velocity and which can be written as F damping is equal to minus B, a constant, into dx dt, that is the velocity. We know that the unit of B from this expression is clear. It is the unit of force divided by the unit of velocity. That is, we can write it as the unit of B as Newton second meter inverse, or in CGS system which is dyne second centimeter inverse. So by observing the values given in the problem, the values of restoring force and the resisting force, we have to write down the values of A and B. Now just comparing the expression of restoring force and the resisting force, we get the values of A is 5 dyne per centimeter and B is 2 dyne second per centimeter from the given data of the numerical. And we know from our earlier knowledge the expression of angular frequency can be written as omega is equal to root over of A by M. So now if we put back the values of A and M there, we get omega is equal to 1 by root 2 radian per second. Similarly, we know the damping constant can be written as 2k is equal to B by M, and therefore k is B by 2m. The value of B is given 2 dyne second per centimeter and the value of M is 10 gram. So we have here, if I put back the value of M as 10, it will be just 1 by 10 second inverse. Just if I compare these two, we can write that k is less than omega. Therefore we can say that the motion is oscillatory, that is the case of underdamped motion. There is another example of problem on oscillation. The problem is given: a particle underdamped harmonic motion follows the equation of motion xt is a e to the power minus 2t cos root 3t in minus pi by 6. We have to find out the amplitude of the oscillation if the particle starts from rest at a distance 10 centimeter from the origin. Now according to the problem, it is given that at t is equal to 0, that is initially it starts from x equal to 10 centimeter away from the origin. So at t equal to 0, x is 10 centimeter. Now using this boundary condition in the given equation, we can write, if I put back t equal to 0 and x as 10 centimeter, we get 10 in the left hand side is equal to a e to the power 0 cos minus pi by 6. As we know, cos of minus theta is cos theta. So in the right hand side we have a cos pi by 6, that is a into root 3 by 2. So just changing the side, we get a equal to root 20 by root 3 centimeter. So by using the values, we have directly calculated the value of amplitude of motion which is 20 by root 3 centimeter.